Hi, my name is Germán Moltó. I'm professor at Universitat Politècnica de València in Spain, and in this video I'm going to introduce the OSCAR framework as part of the AI Sprint runtime environment. The AI application design workflow starts with the application development using the AI Sprint design. Then we have the application deployment, and for this the Toscanizer tool creates the corresponding Tosca templates to describe the cloud application infrastructure on which the services, the AI inference services are going to be deployed on top. And we're going to use the OSCAR and the SCAR framework to run the AI applications along the computing continuum. In this particular video, I'm going to focus on the OSCAR framework. Now, OSCAR focuses on serverless computing for AI inference on the computing continuum. So the problem solved is that we have the ability to deploy OSCAR clusters based on Kubernetes along the computing continuum. It can run on clusters of Raspberry Pis. It can run on dynamically provisioned Kubernetes clusters on a public cloud infrastructure, on your on-premises cloud. It allows to deploy pre-trained AI models for inference on these clusters. These pre-trained AI models are packaged as Docker images, and Docker containers are run on these OSCAR clusters on an event-driven basis. So you can upload files to an object storage and it triggers the execution of the AI inference model or if you create a synchronous invocation, then this triggers the execution of the inference model. So basically provides data-driven enactment of AI inference pipelines involving multiple OSCAR services. So you can have an inference pipeline composed of several services, and some of these services can run on specific OSCAR clusters and other services can run on other OSCAR clusters, even at disparate computing infrastructures, one of low-power devices such as Raspberry Pis and another composed of resources from a public cloud. So the motivation is that deploying and configuring Kubernetes-based infrastructures for running AI models is a complex task. And also executing these AI inference pipelines, like a workflow along the computing continuum, it's a complex task because it involves disparate hardware resources and technologies. So without AI Sprint, deploying these pre-trained AI models requires the integration with multiple event sources. So when you upload files to a certain object store, this triggers the execution of the inference phase of the model. Without AI Sprint, we also face this problem that the scalable AI model inference requires the coordinated and automated deployment of additional computing resources right when they are needed. And this is elasticity. So this means that you need to add additional virtual machines when they are required or additional pods within a Kubernetes cluster in order to cope with increased resource demands during the AI inference phase. And this is typically a complex procedure. Also, manually defining AI inference pipelines is a complex and a task and that can be error prone. So with AI Sprint, with the help of OSCAR, we have the ability to deploy these pre-trained AI models in an OSCAR cluster, and these OSCAR clusters can be dynamically provisioned via the infrastructure manager on multiple cloud backends. OSCAR services can be also deployed using the infrastructure manager on existing OSCAR clusters. For example, if you have an OSCAR cluster running on a set of Raspberry Pis or NVIDIA Jetson or whatever low-power devices you might have. These AI models can be executed in a scalable manner using automated elasticity on cloud platforms, so the cluster can grow and shrink in terms of the capacity needed. Now, this is mainly the OSCAR architecture. So basically, we are using the infrastructure manager to deploy an elastic Kubernetes cluster that is using CLUS, which is an elasticity system developed by the research group. And it monitors the number of pending jobs, pods that need to be executed within the Kubernetes cluster and adds additional virtual machines and removes the virtual machines so that the cluster can scale within the boundaries defined by the user. We are using MinIO, which provides an API compatible with Amazon S3 so that when you upload files to a MinIO bucket, it triggers the execution of a Kubernetes job which runs under this scalable Kubernetes-based infrastructure. But we also support the ability to expose an OSCAR service and offer the ability to make synchronous calls. For this, we're supporting Knative, and Knative provides the ability to perform synchronous invocations to an OSCAR service and add several pods that will cope with these incoming HTTP-based requests. We also have the ability to directly expose an Oscar service outside of the Kubernetes cluster for these models that already provide like a REST API or another interface that can be directly used by the user. So we kind of exposed using a load balanced approach, and the number of pods can grow and shrink depending on the number of requests. Now there is automated data staging from Min.io and from other object storage supported, and the output storage is supported are Dcache, One Data, Amazon S3, and Min.io as well, to provide, let's say, like midterm object storage system. Now, if we focus on the mass detection application, we can have a couple of components. The first one that blurs the faces, that extracts the frames from the videos, and this can be run in an Oscar cluster of Raspberry Pis. This can of course also run on a cluster that can be deployed on a public cloud. And the component 2 performs the mass detection itself out of a pre-trained AI model to detect if the faces wear a mask. And this can run in an Oscar cluster that can be executed in the EGI federated cloud. So you can mix and match disparate computing infrastructures using like an homogeneous approach to perform executing along the computing continuum. So in this case, the cluster of Raspberry Pis is closer to where data is generated, and the output data, the mass detection process, is storing One Data to provide like midterm object storage. So let's focus on a demo of Oscar. And here we'll see that what we're doing is to connect to the web page of Oscar. And we'll see the features. There is a serverless platform for compute-intensive applications. And when we are ready to deploy an Oscar cluster, we are directed to the Infrastructure Manager dashboard. It's a production-ready service that we are operating at the research group. Basically, we are logging through EGI check-in, and by logging through EGI check-in, we have the ability to use our home IDP credentials, for example, from our university or from a Google account or Twitter account. In this case, what we are using is we are registering new credentials to access a certain cloud. In this case, we are accessing the EGI federated cloud, but it could be AWS, Microsoft Azure, Cloud and Heat, or other European cloud providers supported. Now, once we have defined the credentials, we go to this wizard-like experience in which we set the Oscar cluster details, such as the name, the configuration of the front end and the working nodes. Remember that it's a Kubernetes cluster under the hood, so we specify 4 CPUs for the front end, 4 CPUs for the working nodes, the tokens to access the Kubernetes admin panel, then a password to access Oscar and Min.io, and finally an email. Now we specify the cloud provider, so note that with this approach, the user can self-deploy an Oscar cluster on whichever cloud site he or she has access to. Now we submit, and this takes between 15-20 minutes to provision the virtual machines, to deploy Kubernetes on top, and configure all the Oscar services on top. And when it's configured, we just access the endpoint. Notice that we are providing dynamic TLS support, so we provide HTTPS support out of the box. And what we are going to do is to first create a service, because there were no services, of course, available in this newly created cluster. So for that, we are going to use the Oscar CLI, the command line interface. We could also do this through the web-based user interface, and also through the publicly available Oscar API. Now what we are doing is we are registering a new cluster using Oscar CLI. So we basically add the endpoint of the cluster and the username and password that is required to access it. Now we obtain some information about the cluster. We see that this cluster uses in the architecture AMD 64. It's using as the backend OpenFast, and it could also be using Knative, which provides a more scalable approach. support both approaches. Now we log in into the existing Oscar cluster. This is the cluster of Raspberry Pis. This is a cluster that has already been configured, but we need to register this Oscar cluster at the edge of the network into the Oscar CLI so that we can deploy Oscar services on top of this cluster. So again, we specify the endpoint and we specify the user credentials to access the cluster. Now, if we see the information about this cluster, we see that the underlying architecture is ARM64. So we will be running an AI pipeline across disparate computer architectures. Now, in this particular case, we're going to also use the Spring monitoring system. It uses InfluxDB to gather metrics, both infrastructure level metrics and application level metrics. In this case, we take a look at the bucket, which is where the metrics are stored. The bucket is empty. And now it's time to take a look at the workflow definition. Basically, what we have is a functions definition file. It's called an FDL file, where we have the several services. So basically, we have an anonymization and splitting service, which will be running at the edge of the network in the cluster of Raspberry Pis. And then we have another Oscar service, which is running in the Oscar cluster, running in the EGI federated cloud, which will provide the mask detection process on the anonymized images. Now, the way that these services are coupled is that the output of one service is stored in a bucket, and this bucket, this MinIO bucket, triggers the execution of another Oscar service. So by chaining these different Oscar services through buckets, we can compose an AI pipeline. Now, each Oscar service runs, every time it's triggered, a container out of a Docker image that is typically stored in Docker Hub or in GitHub Container Registry. So basically, we execute a script inside this Docker container, and in this shell script, we can do whatever we want that is installed in the Docker image. So in this case, we're using FFmpeg to extract certain images, and for the mask detector service, we are using a Python script in order to use a pre-trained AI model to detect whether the masks are being worn by the people or not. Now we are using the Oscar CLI to apply this workflow. You will see that different services are being created. In this particular case, we have split the service into several services in order to showcase also the usage of the underlying monitoring, but this can be embedded within a single service. So it's just another approach. We're going to check that the services are actually created in both clusters, in both Oscar clusters. So for that, we use the Oscar CLI service list command. And we see the different services created in both clusters. Now what we're going to do is we check through the web-based interface that the services have been created. And we're going to trigger the workflow by uploading a file to the input path. So we are going to upload a video file. And once we upload the video file into the cluster of Raspberry Pis, then it triggers the execution of the service, which is going to extract certain images and do the anonymization, the blurry faces approach. We can see the logs of the job being executed. And by checking the logs, we can understand the time required for each application, and we can see there are some problems in the execution of the script, and we can see how the workflow evolves. And we take a look at the cluster in the cloud. See that the mask detector has been executed, and these are output data results. We can also check the logs of the execution. Now we will connect to InfluxDB in order to see that the data metrics have been ingested. But first, we're going to use a nice tool called Bliss so that we can compare side by side the images available into different MinIO buckets, so that we can check we can compare from the initial images into the output images, each of them side by side. Basically here we're specifying the input bucket and the output bucket and the output folder, and we see that the ones in the right have this bounding box, so that the mass detection procedure has been working as expected. We also see that the output data were automatically ingested into one data. One data is a distributed storage system, typically used for scientific data storage, and we see that the output data files are checked there, and we can download them and see them in more details. Now we go back to InfluxDB, just as we were saying, and we will check that the metrics have been correctly ingested in InfluxDB. We can do queries on top of this data in order to perform aggregated queries to understand the execution time of the workflow. And finally, once we have done, the Oscar cluster is deleted and we terminate the dynamically provisioned virtual machines. And this is done through the Infrastructure Manager dashboard. Now, if you are more interested into this framework, you can check both the Oscar webpage and the GitHub repository for Oscar. It's an open source development under the Apache 2 license. We have also several blog entries, in particular this one that appears in the slide related to the use case that I was showing. And we also have a couple of references in case you want to read an academic contribution. And with this, I finish my presentation. Thank you very much for your interest. Bye-bye.